Okay, let's start. So we started to talk about, can we review question 23 from 6.1? Of course. So let's go. 6.1, 23. K factorial x raised by k over 2k factorial. Can you see it? Okay, you can see it. Okay, we want to find the radius of convergence of each series. All right, so let me write this down. Then we go to whiteboard. So k goes from 1 to infinity, a k factorial square x raised by k over 2k factorial. All right, fine. Actually, you know what? Because this is the second day of power series. Let's just go back to review. Remember geometric series, we know a little bit. And let's just go back to review. Okay. So see, a power series, right, is in this form. Well, this one n starts from 0. So we call n index variable. But in the homework, n started with 1. So basically, the index is up to us. All right, we can forget about a couple of finite terms. So we can always re-index. So we can start from 0. Sometimes we start with 1. Sometimes we can start even with 2, so on and so forth. Okay, so n is called index variable. So n is index. And then the variable is x raised by n. So a subscript n represents some real number. So x raised by n, right? We could see here n, if n is 0, we have a constant term. N is 1, we have x first power. So we have linear. N equals 2, we have quadratic, so on and so forth. Right? So we know polynomial functions, right? So this is like infinite polynomial functions. Polynomial function of degree n, we have a degree n. So the n is a finite number, but here we have n can go up to infinity. All right. So that's the definition of it. And the more, like a more standard term is this one. Right. So we have a c subscript n, just like a subscript n in the other form. We can write as c subscript n, then x minus a raised by n. So what is a? A is a real number. And then we will see if this one converges, right? This one always converges at its center. So a is its center. We call a is the center of this series of convergency. And for this one, this is x raised by n, so we can think as x minus 0 raised by n. So the center of convergence is 0. A power series always converges at its center. Right? There's no surprise, right? Because if it's at its center, right? Think about x equals a minus a equals 0. So we're only left with a constant term. And constant term is a finite number. So that means the series. So series always converges at its center. And then we learn some definitions, right? Something called a radius of convergence. What is that? Let us say x, absolute value of x minus a less than r, this one. Right? We'll have this power series. If we have absolute value of x minus a less than r, and we see the series converges. And the capital letter R is called the radius of convergence. The radius of convergence. And then we have another term called the interval of convergence. Interval of convergence in this form is r plus r minus a to a minus r to a plus r. All right, we can use this real number line to represent. So A represents the series always converges at its center A. And maybe the series converges for all real numbers. Maybe the series converges at a certain interval, right, from A minus R up to A plus R. So I have three situations of convergency. And how do we find the interval of radius of convergence? Right, we basically use the definition, because we need x minus r less than a finite number. Okay, so we use this. And we can represent functions as a power series. We'll see some examples. Geometric series. We know geometric series converges if the ratio, absolute value of the ratio less than 1. And we know exactly what it converges to. So we can use that definition to write like this one, right? If we have 1 plus x, so on and so forth. So basically the summation of n equals 0, x raised by n up to infinity, right? If absolute value of x less than 1, that converges, that's a geometric series. It converges to the first term over 1 minus the ratio, right? Basically, we see this is a rational function. So rational function 1 over 1 minus x can be represented as an infinite series. And now, of course, we can find the radius of convergence and the interval of convergency. Right. We have gone through a couple of examples. Basically, we think of this as a geometric series, and it converges to this function, right? All we have to figure out is the first term A and the ratio R. Okay, so now let's go to 23. Anyone has any questions? Okay, so 23, we have the variable is x raised by k, and the index represented with k. So what do we need to do? We need to follow the definition, right? Definition of series, infinite series converges. And what's the center of this series? 0, right? It always converges at its center. So that means this one converges at 0. And also, what else we need? Let's go to the whiteboard. So basically, we're using the definition of convergency, right? So we have an absolute value of x minus a less than r, right? So it converges when this condition satisfied. And a is 0 in our case. So a equals to 0 in our case. So which means the center of convergence is 0. So what's the other term? The other term we have k factorial, oops. So k factorial square. K factorial square divided by, I'm going to write another one, divided by 2k factorial. Right. oops. So the k start with 1, so the index, let me write this one here. So oops. Index k start with 1, go to infinity, and then we have, let me write it. So k factorial square. We can always write a couple of and 2k factorial. We can always write a couple of terms to get some intuition about this series. So x raised by k. So let's write a couple of terms. So let's see, this one equals to, let's call k starts with 1, right? So k starts with 1, we have 1 square in the numerator. We have 1 square in the numerator, which is just 1. And the denominator we have 2 times 1, which is 2 factorial, we just get half. So the first one is just half of x, right? Because x raised by 1. And the second one we will have, so k equals 2, we have 2 factorial square, 2 factorial square over 2 times 2 factorial, then x squared. So what do we have? 2 times 2 and 4 factorial. And 4 factorial is 4 times 3 times 2. Then that's 1 over 6. So 1 over 6 x squared. Then plus is 3. 3 probably much bigger. So I have a 3 factorial square over 2 times 3 factorial. So 3 factorial, which is 3 times 2 times 1, then square, which is 6 squared. Over the bottom, which is 6 factorial. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. 6 squared in the numerator cancel with this, so 1 over 20. 1 over 20 x cubed. So on and so forth, right? So it's always good to write out a couple of terms. And if you want, you can write more. We can write more couple of terms. All right, so now what do we do? So we see factorial, right? The intuition is we want to use the ratio test. Because ratio test, we can cancel out many terms for factorials. Right? Remember ratio test, we take a limit, absolute value of the n plus 1th term divided by the nth term. Then we will get a limit. Yeah. If the limit is 0, that is to say the series converges for all real numbers. Right? If the ratio equals to infinity, that means it only converges at its center. Right? And maybe the ratio, we can come up with the function of x. Then we can find out the interval of convergency and the radius of convergence. So let's apply that. So we apply ratio test, right? So see, okay, we take a limit, then n plus 1, so absolute value. So we don't really have to do absolute value because we're dealing with factorials, and especially k starts from 1, so everyone's positive, right? So we don't really need to put absolute value, but I already put the other one, so let me just put it. So k plus 1th term, I mean, like, so here we use index k, so k plus 1 term. So we have k plus 1 factorial square factorial square, right? And over, well, x raised by k plus 1. X raised by k plus 1. Okay, let me move this absolute bar. Then divided by 2 times k plus 1. 2 times k plus 1 factorial. Then divided by the kth term, I'm going to write as multiplying by the inverse of the kth term. So which is a 2k factorial divided by k factorial squared. And we will see a lot of terms will cancel each other. So that's exactly why we want to use this. Let's just be consistent and put absolute value sign. Again, we don't really need the absolute value bar here, absolute value sign here, because the k start from 1, we have factorial, everyone is positive. So then the limit k approaches to infinity. Right, so we use ratio test. Now k plus 1 factorial, it's just k plus 1 times k factorial, right? So we have k, so this one we're left with k plus 1 squared. So k plus 1 squared in the numerator. And then k factorial square with this k factorial square will cancel each other. Right? So the factorial will cancel each other. Because k plus, let me write here. K plus 1 factorial equals to k plus 1 times k factorial. Right? Just like a 5 factorial. What's 5 factorial? 5 factorial can be written as 5 multiplied by 4 factorial. So k factorial square cancel with k factorial square here. Then look at this one. So the denominator, we have 2 times k plus 1 factorial, right? Because it was 2k factorial. And also we want to simplify with this. Let me write on the side. So 2 of k plus 1 factorial. Let me put a bracket here. What's this? This one can be written as, that's a small k, 2k, so let's just simplify first. So 2k plus 2 factorial, right? That one can be written right down here. So that's a 2k plus 2 times 2k plus 1 times 2k factorial. Okay, because we have 2 times k plus 1 factorial. So we distribute 2, so we have 2k plus 2 factorial. And 2k plus 2 factorial can be written as 2k plus 2. The next one is 2k plus 1. Then the next one is 2k factorial. Then we see 2k factorial in the denominator cancels out with the numerator 2k factorial. So what's left? So in the denominator, we have 2k plus 2 and 2k plus 1. So everyone else was simplified, right? That's the exact reason why we want to use ratio test. Okay, so now, oh, I left out x term. All right, x term, I left it out. I have x raised by n here, because this is the nth term. And this is n plus I mean k, I'm sorry, not n, no more n here, k, the index is k. So x raised by k plus 1 divided by x raised by k, that's just x, right? This is x. So when we take a limit that has nothing to do with x, we put x up front, right? So this is n approaches infinity. Okay, let's see what do we get for this. So we have polynomial, we have actually quadratic in the numerator, we have quadratic in the denominator. So same degree. So the limit we get the leading term in the numerator, which is k squared, divided by the leading term in the denominator, which is 4k squared. So the limit we get 1/4, right? So what do we have? We have 1/4 x. Of course, this x we want to put an absolute value. The k, this we want to put absolute value because x can be positive, x can be negative, right? X is a variable, but k is positive. Okay, anyone has any questions? Oh, okay. So Damon, you asked this question. Who asked this? Oh, okay, you did. Okay, so the rest is easy, right? Because this one needs to be less than 1. Because remember the ratio test, right? The ratio test says if less than 1 and it converges. Okay, great. So the radius of convergence is just 4 in this case. Okay, anyone else has any other questions? Okay, if not, so we're going to talk about more about, let me take a picture for the attendance. We're going to talk more about power series today. Okay, let's go back to our textbook. Okay, that's red page. So we're going to combine power series by addition, by subtraction. Of course, we do that, right? If a power series converges, if it diverges, we cannot do anything. It's a diverges. If we add two divergence series, it still diverges. But if two power series converges, that means they converge to a finite number. So we can add them, we can subtract them. And we can create a new power series by multiplication by power of the variable or constant, or by substitution. We will see what does this mean. And we can multiply two power series together. We can differentiate and integrate power series term by term. All right, let's see. So previously, let's read this paragraph. So in the preceding section on the power series and functions, we showed how to represent certain functions using power series, like a geometric series converges to a divided by 1 minus r, and then we recognize that can be a rational function. So in this section, we discuss how power series can be combined, differentiated, and integrated to create a new power series. This capacity is partially useful for a couple of reasons. First, it allows us to find power series representations for certain elementary functions by writing those functions in terms of functions with known power series. For example, given the power series representation for 1 over 1 minus x, we can find a power series representation for its differential, for its derivative. And second, being able to create a power series allows us to define new functions that cannot be written in terms of elementary functions. So this capability is particularly useful for solving differential equations for which there is no solution in terms of elementary functions. All right, so only see the first one you see is very powerful already, right? If we have, right, we can write representation for 1 over 1 minus x for absolute value of x less than 1. Right? Then we can differentiate its power series term by term. And that is the derivative of this function, right? Which is 1 over 1 minus x squared. So that means the derivative of the power series term by term is a representation of this function. Right? So that's pretty powerful. So combining power series. If we have two power series with the same interval of convergence, we can add or subtract the two series to create a new power series, right? That's very important, right? Which means if we add two functions, right, the domain has to be coincide. So same thing here. If you want to add two power series, the interval of convergence have to be the same. Similarly, we can multiply a power series by a power of x, or evaluate a power series at x raised by m for positive integer m to create a new power series. Being able to do this allows us to find power series representations for certain functions by using power series representations of the other functions. For example, since we know the power series representation for 1 over 1 minus x, we can find a power series representation for related functions such as 3x over 1 minus x squared, or 1 over x minus 1 times x minus 3. Because we see this one, but we see each one, we can remember partial fractions, right? Partial fractions, both we can use partial fractions to separate this into two parts, two terms. In combining power series, we state results regarding addition and subtraction of power series, composition of a power series, or multiplication of power series by power of the variable. For simplicity, we state the theorem for power series centered at 0. Similarly, results hold for power series centered at any other number. So let's see this theorem. Combining power series. Suppose the two power series cn x raised by n and dn x raised by n converge to the functions f and g, right, respectively, on a common interval I. So three things. First, the power series of addition or subtraction of 2 converges to f plus or minus g on the same interval. For any other integer m greater non-negative and any real number b, the power series, we can multiply the b to the power series x raised by m and cn x raised by n converges to b x raised by m f of x on I, because the series of cn xn converges to f, right? Converges to f. And we see this previously, right? Previously we see we either get a finite number, so f of x is a constant function, or we have experience of f of x being a linear function, right? Maybe we have absolute value of x divided by 4 less than 1, right? Linear inequalities. So we can multiply if one series converges to a function f on the interval I, we can multiply by a real number b and x raised by a non-negative power. Okay, so this is pretty powerful too, because x raised by m is just a finite term, right? So we can always do that. Okay, 3, for any integer, for any non-negative integer and any real number b, same condition as 2. The series cn now we raise b x raised by m raised by n. So what is that? So basically the x raised by n power, so the x becomes b times x raised by m. So we can do that. Converges to f takes b x raised by m as the variable for all x such that bx raised by m is in the, is in this interval. So basically means, okay, the interval is part of the domain of that. Is number 3 okay? Do I need to explain more about the number 3? Think about Cn, Xn converges to F, right? So if we change X to be Bx raised by M, the same as change the variable of function, the variable in function F to F, so it takes Bx raised by M as the input. Okay, so that's the 3 things about it to deal with 2 power series converges to two convergent power series, but converging on a common interval. So I have 3 situations. Addition or subtraction of the 2 series equals to addition or subtraction of the 2 functions on the interval. And for non-negative m and a real number b, and we can always multiply a convergent series to b times x raised by m. And we can always change the variable x to b. So this is like composition of functions, right? b multiplied by x raised by m. So f takes a function as an input. Okay, we're going to skip we're skipping the proofs. We're going to the examples directly. Okay, suppose we have a n x raised by n is a power series whose interval of convergence is from -1 to 1. And suppose that, and the bn x raised by n is a power series whose interval of convergence is -2 to 2. A, find the interval of convergence of the series of an xn plus bn xn. So A, we can do this, right? Because they do have a common interval. The common interval is -1 to 1, right? Bn x raised by n, the interval convergence is bigger than the first one. So they have a common interval. Common interval is from -1 to 1. So B, find the interval of convergence of the series of an 3 raised by n x raised by n. What happens to this? So before it's x raised by n, now the x changed to be 3x, right? 3x. This is just a composition part. So A is the first part, B is the composition, the third part. So A is the first part of this, right? Addition, and B is the third part. So the B x raised by m. In our case, B is 3, x raised by m is just x. So B becomes 3, x becomes 3x. Okay, since the interval for -1, 1 is the common interval of the convergence of series an xn and bn xn, the interval of convergence of series of an xn plus bn xn is -1 to 1, right? And since an xn is a power series centered at 0 with radius of convergence of 1, it converges for all x in the interval -1 to 1. By combining power series by the third part in the power series, the series of an 3 raised by n x raised by n can be written as an 3n absolute, parentheses, 3x inside the parentheses of n. It converges if 3x, right? Because variable is 3x in terms of x now. So 3x has to have the interval, has to be in the interval of -1 to 1. Well, it's divided by 3. So that means the series converges for all x in the interval of -1/3 to 1/3. All right, any questions? Anybody has any questions? All right, so these two, just use a combining power series, right? These two examples. All right. Checkpoint. Suppose ANXN has an interval of convergence of -1, 1. Find the interval of convergence of ANX over 2 raised by n. Okay, everybody try 6.4. -2 to 2. That's very fast. Yeah, that's exactly right. Because x over 2 is in between, is greater than -1, but less than 1. So we multiply by 2. So so the interval of convergence for this one is from -2 to 2. Yes. Okay. Anyone has any questions? Okay, let's keep going. So the next example, we show how to use combining power series and power series for the function f to construct a power series for function related to f. Specifically, we consider function related to function 1 over 1 minus x. And we use the fact that 1 over 1 minus x equals to infinite sum of x raised by n, for n goes from 0 up to infinity. And of course, for absolute value of x less than 1. Right, geometric series. So this example, constructing power series from known power series. So use a power series representation for 1 over 1 minus x, and combine with combining power series to construct a power series for each of the following functions, and find its interval of convergence. So let's say A, 3x over 1 plus x squared, and B, 1 over x minus 1, x minus 3. 1 plus x squared. Okay, so the numerator has 3x. We want to factor out 3x. So factor out 3x, we can write the rest as 1 over 1 minus negative x squared. Now we see 1 over 1 minus negative x squared is beautiful, right? So that means we can, in our head, we can imagine that's an infinite power series. The first term is 1, and the ratio is negative x squared. So as long as negative x squared, absolute value of negative x squared is less than 1, and this series converges, right? So oops. Let's see, using the power series representation for 1 over 1 minus x, and the part 2 and 3. Combining power series, we find a power series representation for f. Okay, for f is given by 3x multiplied by negative x squared raised by n, and n start from 0. Why n start from 0? Because we want the first one to be 1, because in here we say a equals 1. And we just factor out 3x outside. Okay, 3x is 3 is a b, x is x raised by m in a combining power series, right? So a is 1, ratio is negative x squared. So we just read, right, negative x squared raised by n. We want n start with 0 because we want the first term to be 1. And then we multiply by 3x, right? Multiply by 3x. Okay, so then we have x times negative 1 raised by n. So we can factor out negative 1 raised by n from negative x squared. Then we have x times x raised by 2n. Well, x times x raised by 2n can be written as x raised by 2n plus 1. Right? So the function can be represented as this power series. Right? So it's 3 times negative 1 raised by n, x raised by 2n plus 1, which is an alternating series. Let's see if this makes sense. We want to use, so we're combining geometric series property and with combining power series part 2 and part 3. All right. So how is it plus 1 in the exponent? Okay, do you see x? You see here the x here? We have x raised by 1 here. We have this x, that's x raised by 1. And then from here, we have x raised by 2, then raised by n. Right, 2 layers of exponents which is multiplied by. So we have x raised by 2n from here, x raised by 2n, then x, that's x raised by 2n plus 1. Okay. All right, any other questions? Let's see example 2. Oh, okay, let's finish this one. So the interval of convergence of this for the series 1 over 1 minus x is minus 1 to 1. The interval of convergence for this new series is a set of real numbers x such that x squared less than 1. Right? Because that's the ratio. Actually, it's a negative absolute value of negative x squared. Well, absolute value of negative x squared is same as absolute value of x squared, less than 1. So therefore, the interval of convergence is still negative 1 up to 1. Okay, because that's the condition for geometric series, right? The ratio, because in this case, the ratio is negative x squared. So absolute value of the ratio has to be less than 1 to converge. Okay, let's say B. We use partial fraction, right? 1 over x minus 1 times x minus 3. We can write as two rational functions with linear denominators, right? Partial fractions. So we do that, we do partial fractions, we get 1 over half divided by 1 minus x minus half over 3 minus x. So we want to fit into the situation a over 1 minus r, right? That's the formula in our head. A over 1 minus r. A is the first term in the power series, and in the geometric series, and r is a ratio. So half for the first one, half is the first term, right? And 1 minus x, right? 1 minus x. And then for the second one, this 3, we want to change this 3 to be 1. So what do? We factor out the 3. We factor out 3, so the first one becomes 1. Then x becomes x over 3. Then 1 over 3 divided by 3, that's 1 over 6. So we put 1 over 6 in the numerator. So in this, the second one is 1 over 6 is the first term a, and the ratio is x over 3. So then we use the combining power series, right? Half over 1 minus x, we just get a half x raised by n. And because the first term is a half, so we want n to be 0, because x raised by 0 will be 1. 1 times half will be half. That's how we get our first term to be half. And then for absolute value of x less than 1. So that's the first part. Similarly for second part, right? Second part, we have 1 over 6 over 1 minus x over 3. And that one we can write as 1 over 6. Then x raised by n, x raised by 3 is a ratio. First term is 1 over 6. And x raised by x divided by 3 is a ratio. And we can write this way, raised by, so 1 over 6, x raised by x divided by 3 raised by n. And we want the first term to be 1 over 6. So that means n, we want to start with 0. Right? If n is 0, x over 3 raised by 0 will be 1. 1 times 1 over 6, we get 1 over 6. That's how we get our first term. And of course, for absolute value of x divided by 3 is less than 1. Or that is the same as absolute value of x less than 3. Okay, anyone has any questions? So geometric series. All right. Since we're combining those two power series, the interval of convergence of the difference must be the smaller of those two intervals. So we have to find a common interval. So using this fact from the combining power series, so we can rewrite 1 over x minus 1, x minus 3 to be this power series, right? So half minus 1 over, so that's 1 over 6, x raised by n, and we see 1/3 raised by n. So we can write as 1 over 6 times 3 raised by n, then x raised by n. And then so the interval of convergence has to be -1 to 1, because for the first part is from -1 to 1, for the second part is from -3 to 3, and the common interval is -1 to 1. Any questions? For the partial fraction, does it matter which fraction has negative half? Oh, it matters. When you do AB, right? When you do AB, you will get, I don't want to do this calculation. When you do AB, you think, okay, we have A over, let me type in the chat. Remember, we do A over x minus 1 plus B over x minus 3, right? Then we will get a number for A. In this case, A is -1/2, and B is +1/2. You have to go through the calculation. I was just too lazy to go through the calculation. Should we go through the calculation? Oh, okay. All right. Okay. All right, so everyone try this. So now I will try this one too. So 6.5. What's going on? Why we lost 2 people? Okay, so everyone try. Try 6.5. 6.5. I'm going to try myself so we can remember our partial fraction skills. So we have a. Okay, I would suggest you to do 1 over a over 1 minus x plus b over 2 minus x. Okay. All right. Convert to -1 to 1. Okay, I agree with you. What about representation of the function? Yeah. Yes, the interval of convergence, yes, it's from -1 to 1. I agree with you. And let me type my representation. So let's see if we get the same thing. I get a half multiplied by 1 over 2 raised by n plus 1 minus 1 plus half raised by and a half, right? The n goes from 0. Yeah. Yeah. Okay. Anyone has any questions for this one? Should we do this one together? Okay, let's do this one together. So we need to go, right. It'll be a good review for partial fractions also. So we need to remember how to do partial fractions. So we have so we have 1 over, so I'm going to type. So our numerator is 1, our denominator is 1 minus x, 1 minus x, and x minus 2, right? X minus 2. So this one. And we want to represent this one with infinite many power series. We want to represent this one with power series. So we do partial fractions. So partial fractions, we say, okay, this one equals to a divided by a, then b. Oops. So the first denominator, I'll have 1 minus x. And the second denominator, I want to write as 2 minus x. Actually, let's do x minus 2 first. Okay. All right. Okay. Then in the middle, we add those two. So first, partial fractions. We want to separate this one, right? So 1 over 1 minus x and times x minus 2. We can write as some number divided by 1 minus x plus some number divided by x minus 2. So we need to find out a and b. So that means a, so we're going to do common denominators, right? So for a over 1 minus x, we need to multiply x minus 2 divides itself. Then plus b times 1 minus x divides itself. Then that has to equal to 1. Okay, so once we make a common denominator on the right-hand side, we can ignore the common denominator. because if the common denominator is the same, the numerator have to be the same. So the left-hand side numerator is 1, and the right-hand side is a times x minus 2, and plus b times 1 minus x. Now let's separate this. So then we have a times x minus 2a plus b minus bx equals to 1. Right? And this gives us, so a minus b, right? For x term, we have ax minus bx. Well, the right hand side doesn't have x term. That means we have 0x, right? And for the constant term, we have negative 2a plus b equals to 1. So out of this one, we get two equations. Right, we have x term. So ax minus bx equals 0x because there's no x term. That means we have a 0x, right? We can think this way. And the constant term, we have negative 2a plus b equals 1 because we matched up, basically we matched up the left hand side and the right hand side. So this one tells us, did I do a? Yes, okay, a minus b. So that means a equals to b, right? It means a equals b. And if a equals b, I substitute into the second one. Again, negative 2a plus a equals to 1. So that gives me a equals to negative half. So that gives me a equals b equals negative half. So I just plug in here, so I get, so I'm going to rewrite. So that equals to negative half over 1 minus x, right, plus negative half over x minus 2. Right? And I don't like x minus 2, right? Remember, we always have this in our head. Geometric a over 1 minus r, right? A geometric series converges when absolute value of r less than 1, and it converges to this guy, the first term divided by 1 minus the ratio. So we always have this in mind. So we want this one to be 1 minus something. So we're going to rewrite this to be, I'm going to change right here, okay, because it's too much writing. I'm going to change this one to be 2 minus x. If I do 2 minus x, that introduces a negative sign, right? So I have basically I have negative 2 plus x. But if I write 2 minus x, that introduces a negative sign. And the negative become positive. So the top just become positive half. So I have negative half divided by 1 minus x plus half divided by 2 minus x. And also, I don't like 2 minus x. I want to manufacture this one. What do? I factor out 2 from a denominator. I write as 1 minus x divided by 2. So only the denominator. Okay, so this I'm only writing the denominator here. So 2 minus x, I write as 2 times 1 minus x raised by 2. X divided by 2. Then 1 half divided by 2, I can write as 1 quarter. Right? So the second term becomes 1 quarter divided by 1 minus x raised by x divided by 2. I don't know why today I always want to see x divided by something, but I always say x raised by something. Okay, so the second term, we write this way. So now let's take a look at the first one. The first one tells us the first term is just -half. Right? Well, we can do this. Oops. No, let me just write it. It's much easier to write it. So that means this function can be written as quarter over 1 minus x divided by 2. If I'm confusing anyone, please let me know. I will try to explain. Minus half over 1 minus x. Right? Okay. So we see the first one converges. So let's do this one first, right? So we think about the A. A is quarter. Think about this as A. Right? A is quarter. What's the ratio? Ratio R is x over 2. That's the ratio R. Right? And then this one will converge when R, which is x divided by 2, absolute value of it, less than 1. Oops. Right. Which means absolute value of x less than 2. Right. So the radius of convergence for this one is from -2 to 2. Okay, similarly, now let's see the second one. Let's see the second one. So A equals to half, and ratio just R equals to x. Right? So that means for this one, it converges x less than 1. Oops. The radius of convergence is -1 up to 1. So for the combination, the interval of convergence is a common interval, which is -1 and 1. Now, how do we write this function? And we can write this function. So the first one, how do we write it? We write as a summation k or n starts from 0 up to infinity. The first term we want to be quarter. Then the ratio is just x divided by 2 raised by n. And we see this one we can simplify. 1 over quarter just, so let me skip writing this summation sign, okay? So that's a 1 over 2 squared. Right, let me not write this equal sign. So 1 over 4 we write as 1 over 2 squared. And x raised by n, x divided by 2 raised by n, we're going to write as 1 over 2 raised by n, then x raised by n. We have 1 over 2 squared times 1 over 2 raised by n, and of course that's 1 over 2 raised by n plus 2. X raised by n. Right. So the first one, so this one can read as summation of, infinite many terms with 1 over 2 raised by n plus 2, x raised by n, for n start from 0. Right? Because for n start from 0, get the first term to be quarter. So similarly for this one, we can write as summation n goes from 0 up to infinity. The first term is a half right? Then the ratio is just x, so we have a half x raised by n, right? Then we just subtract those. We just subtract those two. Subtract those two, we see we can factor out xn, x raised by n. Give a parenthesis. We can also factor out half because both has half in it. And this term we can write it as 1 over 2 raised by n plus 1 because we already factor out half, 1/2 outside. So this becomes from 1 over 2 raised by n plus 2 becomes half times 1 over 2n plus 1. It's just minus 1 because we have factored out this half up front. So that's it. Then we'll put summation sign here. So n starts from 0 up to infinity. So, oops. So this is the representation of this function. All right. So this one equals to this one. Equals to this one. And the condition of the convergence is from -1 to 1. Okay, does this make sense? Anyone has any questions? We'll need to review this one. All right, so, but do you have any questions, Damon? Oh, I messed up partial fractions? Let's check that. Oh, okay, that's right. Oh, why you even read half? You're exactly right. So I made a mistake here. Great. You see, -2a plus a, that's just -a. -a equals 1. So a equals to -1. Oh, that's much easier. Oh, yes. So a equals to -1. Yeah, I made a mistake. So a and b equals to -1. So all this have to be changed. So this is -1. This is -1/2. Yeah. Oh, Damon. Oh, I see. Yes. Yes. But the interval of convergence is still okay. Let's see if the interval of convergence changes. So a equals -1, b equals -1. From here, so b equals -1/2, but negative become positive. So this one is a half. So this one, okay, this one is a half. Let me make this a little bit wide. So this one is a half. So this one is half. So let's change. So this is a half. So that means this is just 1 over 2 raised by n, with no plus 1. And the second one, so -1. So this is -1. So the first term is just 1. The first term is just 1. So this, we have nothing. So this will have nothing. All right, so that means we don't need to do this. So this is 1 over 2 raised by n plus 1. Yes, to n plus 1. So let me make this skinnier. Okay, so we got to remove this half as a quarter, as a factor. So have first term is 1 over 2 raised by n plus 1, then -1, then parenthesis x raised by n. So the representation for this one is this. It's 1 over 2 raised by n plus 1 minus 1 x raised by n. Then the interval of convergence, let's see. So this one still x over 2. Okay, still from -2 to 2. This one still from -1 to 1. The common interval still -1 to 1. Great. All right. Thank you, guys. Thank you, Paul. Sorry for making the mistake. Okay, any other questions for this one? All right, let's keep going. So let's see this example. Finding the function represented by a given power series. So consider the power series 2 raised by n, x raised by n. Find the function f represented by this series. So what do we want to do? We want to use x raised by n, right, series. Oh, sorry. Okay, now you can see it. Okay, so now we see this one. So this one, we see the x raised by n part, we can represent it as a function, 1 over 1 minus x. Okay, and so we want to find a function represented the series and also determine the interval of convergence. So 2 raised by n, x raised by n can be written as 2x raised by n. And then the corresponding power series can be, a function can be written as 1 minus 2x, because the ratio is just 2x, right? The ratio is 2x. And the first one, n starts from 0, so 2x raised by 0 is 1. So the first term is 1. So the representation of the function can be 1 over 1 minus 2x. Oh, this is pretty easy. And then the ratio has to be, absolute value of the ratio has to be less than 1 for this representation to be able, to exist. So absolute value of 2x less than 1 means the interval of convergence is negative half to half. Anyone has any questions? All right. Okay, let's see this one. Okay, let's all try this one. So find the function representing this series and find its interval of convergence. Okay, are we all trying this one? X raised by n over 3 raised by n. We see the ratio right away, right? The ratio is x divided by 3. And we see the first term is just 1 because n starts from 0. So geometric series is saying that's 1 over 1 minus x divided by 3. And we need x divided by 3 less than 1. Hope everyone is trying it. And so far, okay, some of you are really quiet. Okay, I hope I'm not confusing you. I hope you understand me and you know what to do. Okay, anyone has the answer yet? What's the function? Golem has it. Golem says that's a 3 over 3 minus x, and the convergence interval of convergence is from -3 to 3. Shahaya has the same thing, 3 over 3 minus x. The interval of convergence, yes, statement -3 to 3. Okay, Paul got the same thing. Yes, I agree with you. Yes, right? The function is 3 over 3 minus x. Because we get a 1 over 1 minus x divided by 3, we can multiply 3 for everyone, right? The interval of convergence is -3 to 3. Yes. Okay, let's go to the whiteboard to do it anyway. So we can rewrite as this. X divided by 3 raised by n. Because 1 over 3 raised by n is 1/3 raised by n, right? So we can rewrite the series as x over 3 raised by n. And right away we recognize this is a geometric series, right? And this converges to, well, what's the first term? First term start from n start from 0. Anything raised by 0 is 1. So the first term is 1. And what's the ratio? The ratio is x divided by 3. And this converges. For this representation to be valid, we need x divided by 3, absolute value of it, less than 1. Okay. So for this one, we simplify this representation. So what do? We'll multiply 1. So this one is 3 over 3. So basically we multiply every term over 3. So numerator 1 times 3, that's 3. And denominator 1 times 3, that's 3. And x divided by 3 multiplied by 3, that becomes x. So this is a function representation, right? Rational function. And then the interval of convergence comes from here. That means absolute value of x less than 3, which means the interval of convergence from -3 up to 3. Or sometimes maybe they ask you the radius of convergence. The radius of convergence is just 3. And what's the center? The center is 0. Okay. Anyone has any questions? Okay, let's go back to our textbook. Okay. Let's see this. So recall the questions post in the chapter opener about which is the better way of receiving payouts from lottery winnings. We now revisit these questions and show how to use this series, compare values of payments over time. With a lump sum payment today, we will compute how much future payments are worth in terms of today's dollars, assuming we have the ability to invest the winnings and earn interest. The value of future payments in terms of today's dollars is known as the present value of those payments. Let's see this one. You know what? Let's forget about this one. Okay, let's go to this multiplication of power series. So let's see, we have two. We can also create a new power series by multiplying two power series. Being able to multiply two power series provides another way of finding power series representations of functions. The way we multiply them is similar to how we multiply polynomials. For example, suppose we want to multiply cn xn with dn xn. It appears that we just multiply those two, right, series. And we have to multiply term by term. So we get c naught, d naught, so on and so forth. Just like multiplying polynomials, but this is infinite many polynomials. So in multiplying power series, we state the main result regarding multiplying power series, showing that if cnxn and dnxn converge on a common interval, then we can multiply the series in this way, and the resulting series also converges on the same interval. So multiplying power series. So this is saying let En to represent all those terms. So En can be represented as a power series of ck dn minus k term. Oh, okay. Right. This is seeing the pattern of this, right? So En basically the product of all the nth term. So C0, C1, C2, up to Cn, then multiply by dn minus 1 down to d0 term. So this, because you see the index, all adds up to n. 0 plus n, 1 plus n minus 1 is n, 2 plus n minus 2 is n minus 1 plus 1 is n plus 0 is n, right? So all the indexes are n, so we get an En term. So we use this En term to represent this. And the k goes from 0 up to n. C, the index of C increases, the index of D decreases. So just use this representation. So Cnxn multiplied by Dnxn can be represented as Enxn with the En defined as above. Any questions? So for this one, just understanding where does En come from, all right? So that's a definition of En. If it's confusing, you can start, with the finite terms, right? You can start, you think about, okay, E3. So E3, you will get a multiplication of C0, D3, plus C1, D2, plus C2, D1, plus C3, D0, right? Because it adds up to 3. Okay, let's keep moving. And the product series converges to f multiplied by g on the same interval. Right. So the series Enxn is known as the Cauchy product of the series of Cnxn and Dnxn. Right? If you're not math majored, you don't care about Cauchy product. We omit proof of this theorem as it's beyond the level of this test and is typically covered in a more advanced course. We now provide an example by this theorem by finding the power series representation for this. So 1 over 1 minus x times 1 minus x squared. And we see two geometric series, right? 1 over 1 minus x and 1 over 1 minus x squared. Okay, that's here. So 1 over 1 minus x, that's this infinite many power series. And 1 over 1 minus x squared, the ratio is just x squared. So we have x raised by 2n, right? And of course, for both, absolute value of x is less than 1. And both the interval is from -1 to 1. So to construct the power series for this on the interval -1 to 1. Okay, we want to construct f of x equals 1 over 1 minus x, 1 minus x squared. We're going to do the same thing. We need to find a and b, right? We multiply those two, because the first one can be why it says construct the power series for this? No. Oh, okay. So basically, this is the multiplication of 1 over 1 minus x times 1 over 1 minus x squared. Yeah, great. Yes, so we can multiply those two. So the first one is just 1 plus x squared, so on and so forth, where the power is just raised by 1. And the second one, the power raised by 2, because the ratio is x squared. So we see 1 plus x squared plus x raised by 4, so on and so forth. So multiplying, so the f of x can be represented as the multiplication of two infinite series. Right? And we can write out a couple of terms. Write a couple of terms, we have, we have something like this. Then we combine like terms. We will have 1 plus x plus 2x squared plus 2x cubed plus 3x raised by 4 plus 3x raised by 5, so on and so forth. Since the series for 1 over 1 minus x and 1 over 1 minus x squared both converge at the interval -1 to 1, so the product of the series also converges at the common interval from -1 to 1. All right, so that's it. Okay. All right. Power series for 1 over 1 minus x. Power series for 1 over 1 minus x squared. So 1 over 1 minus x times 1 over 1 minus x squared can be represented as a product of two power series. And the interval of convergence is a common interval of convergence for both of them. Any questions? Okay, let's keep moving. Okay, let's all try this one. This is 1 over 1 minus x squared. This one actually is easy, right? Because we already know. We got 1 plus x squared plus then what? Then square. Because 1 over 1 minus x, the power series is 1 plus x squared plus x cubed plus x raised by 4. Well, then we just square this. All right, and then also we have another representation for this same thing. So that's by differentiating. Okay, so we can differentiate in a power series, we can integrate in a power series. So let's see if we have power series represented by f of x, right? We have c0, c1x, c2x squared. So we can differentiate term by term. Differentiate c0, right? It becomes 0. So c1x becomes c1, or c2x squared becomes 2c2x, so on and so forth, right? And of course, we can integrate also. We integrate, we add a constant term. The c0 integrate becomes c0x. c1x becomes c1x squared divided by 2. c2x squared becomes c2x cubed divided by 3, so on and so forth, right? Because it's a polynomial-like, so we can differentiate, we can integrate the term by term by using power rule for each. So term by term, all right. So what do we get? So the differentiation, so if we start with cn x minus a raised by n, we differentiate, so f prime of x would be n times cn x minus a raised by n minus 1, right? Very nice form. Integration, same thing. So when we integrate, we add c term, and then cn multiplied by x minus a raised by n plus 1, then divided by n plus 1, right? Power rule. Let's see an example. So use the power series 1 over 1 minus x and find the power series representation for 1 over 1 minus x squared. We already did one, right? We already did one by product of two power series. And also we can use differentiation. So B, use the result of part A to find to evaluate the sum of series n plus 1 divided by 4 raised by n. Let's see this one. So 1 over 1 minus x squared is the derivative of 1 over 1 minus x, right? So what we can do is we just differentiate 1 over 1 minus x. We can differentiate term by term. Then we would get a 0 plus 1 plus 2x plus 3x squared, so on and so forth. And we see the pattern is just for n term, this is n plus 1 x raised by n. So that means we can represent it with an infinite power series starting from n equals 0, because n equals 0 will give us the first one, 1. So that's it. So n plus 1 x raised by n is the representation of 1 over 1 minus x squared. You see this one is might be different from this, oh, we didn't finish the other one. You could try on your own, all right? You try on your own for this one to use a product of 2. Oh, it should be the same. It should be the same. It should be the same, right? You see this one square. So basically we have this one square. Right? We have 1 times x. Then we have x times 1, right? We see that gives us 2x, so on and so forth. So for x raised by 1, we have 2x raised by 1. So 2 is 1 plus 1, x raised by 1. So we see n plus 1, x raised by n. Okay, so the two different ways will give us the same, exactly the same thing. Okay, now let's see B. So we know 1 over 1 minus x squared can be represented as n plus 1 x raised by n. Now we can use this for n plus 1 divided by 4 raised by n. So n plus 1, 1 over 4 raised by n. We just think 1 over 4 raised by n. In this case, is x raised by n. So we just get 1 over 1 minus 1/4 squared. So we get 1 over 1 minus quarter squared. 1 minus a quarter is 3/4. So we get 3/4 squared, which is 1 over 9 over 16. Well, 1 divided by 9 over 16 is 1 multiplied by 16 over 9. So we get 16 over 9. All right, any questions? So basically, this one, we're using differentiation because we recognize G is a derivative of F. That means we can differentiate the power series because we can differentiate term by term. Then we find a pattern, we write it as infinite sum of n plus 1 x raised by n, and we start n with 0. And we can use this to evaluate a specific x. So in this case, x equals 1/4. That x equals 1/4. We just plug into the function. It seems like f of 1/4. We just plug into the function that's 1 over 1 minus quarter squared to get 16 over 9. Anyone has questions? Okay. Okay, let's all try this one, 6.8. So differentiate series 1 over 1 minus x squared term by term to find the power series representation for 2 over 1 minus x raised by q. So basically we differentiate this, right? So if this is f prime, if 1 over 1 minus x squared is f prime, we're trying to find f double prime. So f double prime, we would have 2 times 1 over 1 minus x cubed. Actually, -2, right? -2, 1 over 1 minus x cubed, then -1 cubed. or negative, negative become positive. So we can write off a couple of terms. All right, you know what? You try this on your own later on. Okay, I want to finish the integrating power series. It's very similar. You know what? Let's leave for next time because we don't have enough time. We only have 4 minutes. So for this one, we can just write the terms, write a couple terms. The first term will be 1, because n equals 0. We have 0 plus 1, x raised by 1. No, x raised by 0 will be 1. So we have 1 plus, then n equals 1. 1 plus 1 is 2, x raised by 1. Then 3x squared, then 4x cubed, so on and so forth. So when we differentiate this, we just differentiate term by term. Derivative of 1 is 0, derivative of 2x is 2, derivative of 3x squared is 6x, derivative of 4x cubed is 12x squared, right? So on and so forth. So we see what's the pattern. So 2, so the first one is 2, second one is 2 times 3. Second one is 2 times 6, which is 2 times 2 times 2 times 3, 2 times 6. Oh, let's do the third one. The third one, 5x raised by 4, will be 20x raised by 3. So what's the pattern? So how do we write? So 2 is n equals 0. X is n equals 6x, x n equals 1. And 12x squared, so n equals 2. So how do we write a function for this? When n equals 0, f of 0 is 2, f of 1 is 6, f of 2 is 12, f of 3 is 20. So let's see the difference. So 6 to 2 difference is 4. 12 to 6, that's 6. 20 to 12, that's 8. So it's not a linear function, right? It's not a linear function. So then it's a quadratic function. So the second level, 6 to 4, that's 2. 8 to 6, that's 2. So it's a quadratic function. So it should be, let's see, n times n plus 1. Let me try n times n plus 1. So when n equals 0, n plus 2. When, oh no, I cannot do n times n plus 2. I better do n plus, let me see, n plus 1. Because the first term is 2. So the first time we have to get a 2. N plus 1, n plus 2. So if n plus 1 times n plus 2, when n is 0, we get 2. When n is 1, bingo, it is. So this one, the representation is infinite sum n plus 1 times n plus 2, x raised by n. Right, n start from 0 to infinity. All right, does this make sense? You see, when n equals 0, so what did I do is I differentiate term by term to find the pattern. So I differentiate it 1, that's 0, 2x, that's 2, 3x squared, that's 6x, 4x cubed, that's 12x squared. Then how do I get a function to represent all those? So I find out is n plus 1, n plus 2. Because the first layer of difference is not constant. So the second layer is 2, it's a constant change. So that means it's a quadratic function. So n plus 1, n plus 2 works. That gives us the right coefficient. All right, anyone has any questions? So we're going to talk about integration for next term. Okay, we can integrate term by term. I'm going to assign some homework. And I see you on Thursday then. Have a good night. Let me stop recording this.